Before we continue with Docker networking, I think it would be better for us to learn Docker terminologies. It's like Cisco, VMware, and Windows. They have their own terminologies that you need to know and get familiarized with, or else you will be lost in the world of Docker networking technology. Let's start with the Docker platform. Docker provides the ability to package and run an application in a loosely isolated environment called a container. The isolation and security allow you to run many containers simultaneously on a given host. Containers are lightweight because they don't need the extra load of a hypervisor, but can run directly within the host machine's kernel. This means you can run more containers on a given hardware combination than if you were using virtual machines. You can even run Docker containers within host machines that are actually virtual machines. And that's what I'm doing now, using 3 Ubuntu virtual servers on a GNS3 Virtual Machine running on VMware Workstation Pro 16. Docker Engine. Docker Engine is a client-server application with the following major components. A server, which is a type of a long-running program called a daemon process. A REST API, which specifies interfaces that programs can use to talk to the daemon and instruct it what to do. It can be accessed by an HTTP client such as wget or curl, or the HTTP library, which is part of most modern programming languages. A command line interface client, which uses the Docker REST API to control or interact with a Docker daemon through scripting or direct CLI commands. The daemon creates and manages Docker objects such as images, containers, networks, and volumes. Docker architecture. Docker uses a client-server architecture. Docker client is the primary way that many Docker users interact with Docker and can communicate with more than one daemon. When you use commands such as docker run, it uses a Docker API and sends these commands to Docker daemon, which carries them out. The Docker daemon listens for Docker API requests and manages Docker objects such as images, containers, networks, and volumes. A daemon can also communicate with other daemons to manage Docker services. A Docker registry stores Docker images. Docker Hub is a public registry that anyone can use, and Docker is configured to look for images on Docker Hub by default. You can even run your own private registry. Images. An image is a read-only template with instructions for creating a Docker container. Often, an image is based on another image with some additional customization. For example, you may build an image which is based on Ubuntu image but installs the Apache web server on your application as well as the configuration details needed to make your application run. Containers. A container is a runnable instance of an image. You can create, start, stop, move, or delete a container using the Docker API or CLI. You can connect a container to one or more networks, attach storage to it, or even create a new image based on its current state. The container networking model. The Docker networking architecture is built on a set of interfaces called the Container Networking Model, CNM. The philosophy of CNM is to provide application portability across diverse infrastructures. CNM is built on three main components: Sandbox, endpoint, and network. A sandbox contains the configuration of a container's network stack. This includes the management of the container's interfaces, routing table, and DNS settings. An implementation of sandbox is the Linux network namespace. A sandbox may contain many endpoints from multiple networks. An endpoint joins a sandbox to a network. The endpoint construct exists so that the actual connection to the network can be abstracted away from the application. This helps maintain portability so that a service can use different types of network drivers without being concerned with how it's connected to that network. Network. The CNM does not specify a network in terms of the OSI model. An implementation of a network could be a Linux bridge, a VLAN, and so on. A network is a collection of endpoints that have connectivity between them. CNM driver interfaces. The container networking model provides two pluggable and open interfaces that can be used by users, the community, and vendors to leverage additional functionality, visibility, or control in the network. Container networking model, CNM, have the following drivers: network drivers and IP address management IPAM drivers. There are two types of networking drivers: native and remote network drivers. The native network drivers are a native part of the Docker engine and are provided by Docker. They are host, bridge, overlay, and Mac VLAN. Remote network drivers are network drivers created by community and other vendors. There are two types of IP address management drivers: native and remote IP address management drivers. Native IP address management driver provides default subnets or IP addresses for the network and endpoints if they are not specified. IP addressing can be manually assigned through network, container, and service create commands. Remote IP address management drivers also exist and provide integration to existing IP management drivers tools. Linux Network Fundamentals. The Linux kernel features is mature and efficient in the implementation of the TCP/IP stack, including VXLAN and packet filtering. Docker networking uses the Linux kernel's network stack as low-level primitives to create higher-level network drivers. There are several Linux networking building blocks which Docker uses to implement its native CNM network drivers. It includes Linux bridges, network namespaces, bit pairs, and IP tables. The combination of these tools implemented as network drivers provides the forwarding rules, network segmentation, and management tools for dynamic network policy. The Linux Bridge. A Linux bridge, Docker 0, is a layer 2 device that is the virtual implementation of a physical switch inside the Linux kernel. It forwards traffic based on MAC addresses, which it learns dynamically by inspecting traffic. A Linux bridge is not to be confused with the Bridge Docker Network driver, which is a higher level implementation of the Linux bridge. Network namespaces. A Linux network namespace is an isolated network stack in the kernel with its own interfaces, routes, and firewall rules. It is a security aspect of containers on Linux, used to isolate containers. Network namespaces ensure that two containers on the same host aren't able to communicate with each other, or even the host itself unless configured to do so via Docker networks. Typically, CNM network drivers implement separate namespaces for each container. However, containers can share the same network namespace or even be a part of the host network namespace. The host network namespace contains the host interfaces and host routing table. Virtual Ethernet devices. A virtual Ethernet device, or VET, is a Linux networking interface that acts as a connecting wire between two network namespaces. A VET is a full duplex link that has a single interface in each namespace. Traffic in one interface is directed out the other interface. Docker network drivers utilize VETs to provide explicit connection between namespaces when Docker networks are created. When a container is attached to a Docker network, one end of the VET is placed inside the container and the other end is attached to the Docker network. IP tables. IP table is the native packet filtering system that has been part of the Linux kernel since version 2.4. It's a feature-rich Layer 3 and Layer 4 firewall that provides rule chains for packet marking, masquerading, and dropping. The native Docker network drivers utilize IP tables extensively to segment network traffic, provide host port mapping, and to mark traffic for load balancing decisions. Docker Native Service Discovery. Docker uses embedded DNS to provide service discovery for containers running on a single Docker engine and tasks running in Docker Swarm. Docker Engine has an internal DNS server that provides name resolution to all of the containers on the host in a user-defined bridge, overlay, and MAC VLAN networks. Each Docker container or task in Swarm mode has a DNS resolver that forwards DNS queries to the Docker Engine, which acts as a DNS server. Docker Engine then checks if the DNS query belongs to a container or service on networks that the requesting container belongs to. If it does, then Docker Engine looks up the IP address that matches a container, task, or service name in its key value store and returns that IP or service virtual IP back to the requester. Service discovery is network scoped, meaning only containers or tasks that are on the same network can use the embedded DNS functionality. Containers not on the same network cannot resolve each other's addresses. Additionally, only the nodes that have containers or tasks on a particular network store that network DNS entries. This promotes security and performance. If the destination container or service does not belong on the same network as the source container, then Docker Engine forwards the DNS query to the configured default DNS server. Now that we know some of the basics of Docker networking, we can move forward and continue to perform some of their tutorials. Stay tuned for my next video.